All right, I want to talk about two different kinds of collisions. There's elastic collisions, which is what it sounds like. It's like when things bounce off of each other. And then there's inelastic collisions which aren't elasticy, like if you have two clumps of clay and they hit into each other and they stick together. And one thing about collisions is that they're really quick events and there are big forces involved because the momentum's changing over a really short period of time. So the forces are really big. And so what that means is if you have, say, friction or drag, you can ignore those at least for that small duration of the collision because the really important big forces are the ones involved in the collision. So, I always come back to this mosquito example. If you have a mosquito that's being hit by a car, it's not going to be like, well, there's drag, so maybe I'll be fine. Like, no, you're gonna see the change in momentum of the mosquito really quickly, and so there's a huge force on the mosquito, and it'll get smashed. So you can ignore forces like drag and friction and other forces that are sort of tickling the object while it's being smashed or bumped by this collision. Now, if we can ignore all these other forces, what has to be true about the total momentum of the system? So for this little lesson, we're going to consider a collision between two objects. And what has to be true if there aren't any outside forces like drag or friction on the object? Well, we have conserved momentum, so it's conserved, which means the change in the momentum is equal to 0. And at least for this lesson, we're only going to look at the change in the momentum in the x direction, which is 0. And if we want to write this for two objects in the x direction in terms of their masses and their velocities, we can write this as, so this is in the x direction. We have m1 v1 x initial plus m2 v2 x initial is equal to m1 v1 x final plus m2 v2 x final. And throughout the rest of this, I'm going to leave off the x's because we're just looking in one dimension, so all the v's are going to be in the x direction, but I just wanted to write it at least in this first equation. So as I said, there's a special kind of collision. There's an elastic collision when things are all bouncy. And in an elastic collision, something special happens, which is that the kinetic energy is also conserved. So you have the momentum conserved and the kinetic energy is conserved. And so for one dimension with two objects, what that means is the kinetic energy of object 1 plus the kinetic energy of object 2 initially is equal to the kinetic energy of object 1 final plus the kinetic energy of object 2 final. So the total energy from the beginning is equal to the total energy at the end. The energy is conserved. The change in kinetic energy is conserved. And this isn't always the case. If you have an inelastic collision, you don't have kinetic energy being conserved. Instead, you'll actually lose some kinetic energy in the process. Now, in the pre-reading, we defined kinetic energy as K for a particular object that has mass m. The kinetic energy is 1/2 m v squared. Now, the rest of what I'm going to be doing in this little lesson is I'll be using the conservation of momentum and the conservation of energy to come up with a really useful formula when you have two objects that are bouncing off each other that relates the relative velocity initially to the relative velocity finally. So what's the rest of this is going to be a bunch of algebra, and I'm going to do it all for you. But if you want to fast forward to the end and just look at the algebra on your page, that's completely fine. But let's start by writing this kinetic energy equation using this, so in terms of the mass and the velocity. So what we'll have is we have 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared is equal to 1/2 m. Let's get this out of our way. Sorry about that. 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And so now we've just rewritten that the initial energy is equal to the final energy. And now what we can do is we can rearrange this a little bit so that we get all the velocities for the one object on the left and all the velocities for the two object on the right. So we have 1/2 m1, so this is just rearranging. 1/2 m1 v1 initial squared minus v1 final squared is equal to 1/2 m2 v2 final squared minus v2 initial squared. And there's a little mathematical trick we're going to use now, which is if you ever have a squared minus b squared, you can actually write this as a plus b times a minus b. If you FOIL this out, you'll see that you get that. So we'll use that little mathematical trick. Sorry, I missed a parenthesis there. And this will go to 1/2 m1 v1i minus v1f times v1i plus v1f, and then the same thing over here where we have v2f minus v2i times, and let me just box this to get it out of the way, v2f plus v2i. Okay, so now what we want to realize, so this is our energy equation. So here we go. This is just energy. And then what we can do is we can rearrange our momentum equation up here, this momentum equation, where we can get all the velocities for object 1 on the left and all the velocities for object 2 on the right. So let's do that down here. So let's bring this down here and rearrange it. What we get is we get m1 v1 initial minus v1 final is equal to m2 v2 final minus v2 initial. Okay, so then this one is our rearranged momentum equation. Now what we're going to do is, I don't know if you've done this mathematically before, but you can actually divide one equation by another equation. And well, first what we'll do is, in this equation, let's multiply both the left and the right-hand side by 2 so that we can get rid of these 1/2s. Now, if you notice, this and this are equal, and then on the right-hand side, we have this and this are equal. So we can divide our energy equation by the momentum equation. So energy divided by momentum equations. And what we'll get from that is we'll get this basically is canceled by this, and this right here is canceled by that, and that gives us just v1 initial plus v1 final is equal to v2 initial plus v2 final, and this can be rearranged to give you v1 initial minus v2 initial is equal to minus v1 final minus v2 final. And if you'll notice, this right here is the relative velocity initially, and this is the relative velocity finally. So for any situation where you have two objects that are elastically colliding with each other in one dimension, you'll find that the relative velocity initially is equal to the negative relative velocity finally. So this is, I should have put a negative sign right there, negative relative velocity finally. So this is just going to be a really useful equation, and you don't have to worry too much about the derivation I just did. I just wanted to see you to see how we got it, but it'll definitely be useful when you're doing problems on homework and things like that. So I hope that was helpful.